covered by finitely many. Sometimes you add the phrase finite type, but this I will take for granted. By finitely many, affine neighborhoods, or affine sets. Sets which, when endowed with the obvious restriction of the sheaf on the full space, are isomorphic as such, of such objects, to affine varieties, which we understand. So this, even complicated, should make sense. Exercise. This exercise is not about the sheet structure. It is just about the fact that we have a space covered by finitely many Noetherian subsets. Every variety as topological space is Noetherian. Oh, I was corrected for mispronouncing and miswriting the plural of sheaves. I didn't do it again. Okay, good. Maybe another exercise. This one will be more demanding in time, but as easy. We know that product exists in the category of affine varieties, which is the same as the category of affine varieties with sheaf morphisms, and it extends. Products, categorical products exist in the category of pressures. So, why is that important? Obviously, it is important for us for very good reasons, because we want to discuss groups. Well, actually, the groups that we will discuss will always be affine. But we would like to discuss group actions. So this involves some G times V mapped to V thing. So we need products, but actually we need it for a more fundamental reason.
For sheaves or for varieties?
For varieties. Thanks. I was so proud. Okay. So our object as topological spaces with the Zariski topology are never housed of, unless they are finite or something like that. So we should not expect the house of property per se, but of course maybe exercise. This is just for preparation. Topological space is housed of, or maybe this is a way to phrase the house of property, if and only if, for the space X, the diagonal is closed when here you have product topology. In our category, the product of objects doesn't give the product topology, right? But with the replacing product topology here with the natural product arising in our product construction, we can phrase this axiom, this house of axiom once again, and define a sheaf, or sorry, a variety is a play sheaf. This is a play variety.
A variety is a variety.
Yeah.
The other way around.
Well, it's a symmetric. It's English. I'm defining that notion, and it is such an object such that the diagonal is closed in x times x, and this is, of course, the Zariski topology. Or, I mean, the topology involved. I'm writing Z topology just to emphasize this is not a product topology. So it has this separation property. So, for example, I think that in his exercise, Miel showed at some point that the stabilizer of point for a group action is an algebraic variety, is an algebraic subgroup. And he used a term GV minus V when did this, relying on some affine structure or linear structure on varieties. One can replace this argument by using the house of X in general. So, okay, before proceeding with the group action, let me give you some examples. We deserve that. Why does one develop this theory and recovery? Examples of varieties. And I leave it as an exercise to properly define the notion, etc., and prove that these are varieties. P and K, which you're supposed to know how to cover with copies of A and K. Well, maybe I should. I don't think it's right. As a closed subset of a variety, as naturally the structure of varieties. Terminology, closed subsets of a fine space the affine space AN are called affine varieties. Somehow you may feel there is this is misleading terminology. We regard the affine varieties as some more abstract thing, but obviously the affine varieties that we regarded so far are all isomorphic to closed subsets of affine varieties. The same way that every fine generated algebra is a surjective image of a free algebra of polynomials. So affine variety is a closed subset of a fine space. Closed subsets of the projective space of whatever dimension are called projective varieties. Of course, these classes are classes that come about most in our study, but not only this. Something that I will not touch, but maybe I cannot not mentioning, is that as we know that projective space is compact in the usual topology, in the Hausdorff topology, it has also a similar property for the Zariski topology that you have to rephrase. Actually, all our varieties are compact in some sense. They are all covered by finitely many pieces, but one can phrase compactness using maps in a certain way and arrive at a property called completeness for varieties, and the projective space, and also every projective variety has it. It is complete. So this is something that one should remember. You will need compactness properties of such varieties at some point for the Zariski topology. Check the definition of completion. Complete variety. These are complete varieties. Open sets of varieties are varieties. With the restricted structure on them, and open sets of affine varieties, there's a special name for these, called quasi-affine. Open sets of projective varieties called quasi-projective. Maybe I should mention, if you have an affine variety, there is a notion of principal open sets. These are the sets which are non-zeros of some regular function. And these, Miel will talk about it, these form a basis of the topology. So every open set is a union of principal open sets. The principal open sets themselves, a principal open set of an affine varieties, is not just quasi-affine. It is quasi-affine, of course, by definition, but it is actually a affine variety by its own right. Due to the process of localization, one can force an inversion of this specific function that defines this principal open set. And this will make our principal open set isomorphic as a variety to some affine variety. Okay? So principal open sets in affine varieties are actually affine varieties. But not every open set of an affine variety is an affine variety. An example would be, take the first example is take A2 minus 0, 0. This is an open set in an affine variety which is not affine by its own right. It is quasi-affine, of course, by definition. Is this clear? So these two properties together, last two properties, just to summarize, locally closed subsets or subset of a variety is a variety. The union of such is not necessarily a variety. Constructible set is not necessarily a variety, but it is something very close to it. Okay. So obviously I can now define for you the notion of an algebraic group as a group object for varieties. I will not do so. I will just restrict myself to the study of affine algebraic groups. So an affine algebraic. I'm defining an action, algebraic group G. And the variety P, we say that G acts on V. You know G acts on V, or that V is a G variety. What should happen now? If there is a map, actually not implicit in the structure, this should be part of the action. G times V to V, satisfying just morphism of varieties. Which defines the group. If you wish at this point, it is defined a group action on the set V. We look at the points. Or such that it gives a group homomorphism into the automorphism of V as an algebraic variety. This is the same. Okay, we've seen several actions, so I will not give many examples of this. GL2 act on P1, GLN act on Pn. This is an action of an affine group on a variety. Also GLN act on AN, this is clear, with the usual action. This is clear, this is actually an affine action, but also this one. This is not an affine action anymore because this is not an affine variety, but obviously I want to consider it. This is how an orbit looks like in here. And we've seen in our discussion already, so the first talks, such objects are important. So here's an exercise for you. Show that every morphism of varieties is constructible. To take constructible sets, in particular, start with this. The image of a constructible set is a constructible. The image of the domain is constructible in the target. And if this is the case, then also the image of every locally closed subset is constructible in the target, because locally closed subsets are isomorphic to varieties by their own right. But the image of any constructible set is the union of the images of locally closed sets, so it can be constructible as well. So this is how you prove it. I mean, but of course you will have to reduce it to the affine case. theorem property. It shouldn't be hard. So, corollary. Every action understood as well as the left is constructible. In particular, orbits are closed, are locally closed. And passing to a new category, maybe let me pause for a while here and say I haven't discussed, I haven't explained, but I hope it is obvious, the Hausdorff topology on a variety. I define, this is the classical definition, this is the classical definition of variety, and but we know, maybe I should add this mark. Exercise. Define the H topology on a variety. Maybe one should call it analytic topology because it need not be Hausdorff actually. But this is topology that you would define out of the gluing process. I keep calling it the H topology though, using the topology that we have on pieces. Check that the H topology on a variety is indeed Hausdorff. Of course, this exercise makes sense under the assumption that we had last time, yesterday, that our field has its own absolute value topology. Most of what I'm saying here is very general and applied for very general or for any algebraically closed field. But in our mind, we always have the field C or CP, etc. And we also have this topology. And think about this topology and considering the Borel structure associated with the Hausdorff topology, we get that the action is taken. Actually, from all this theory, this is what we really want. And this is why I emphasize and bother to prove in details this Chevrolet-Tarski theorem, even though I could have taken it as a black box. This is very important in theory. And now I'm about to present another very important theorem, very standard, and if I had one more hour, I would give a proof, but I think I would skip the proof, the standard, very standard proof of the following theorem. This is the theorem of Chevrolet about existence of coset space. I already said that one of the motivations for us to define varieties in general is in order to, when we study subgroups of a group, we need the relevant dual object of coset space, G acting on G mod H. And these form general varieties, not defined varieties, but one should explain why I didn't just list in this list of example G mod H. One should explain why these guys exist. And Chevrolet did it. For G, a finite group, H, a fine subgroup. So Z close up. There exists a variety G mod H that theoretically isomorphic. So I'm using G mod H as a name to this variety. So isomorphic to the relevant Hausset space. Actually more than that. If you consider the Hausset topology, this isomorphism, we have the natural quotient topology on G mod H, and this isomorphism will be topological as well. And base point. Just the cost H, let me give the name now. G mod H. There is maybe G. Satisfying the following universal property. So a Hausset space could be defined theoretically when I think of groups acting on sets. A Hausset space has some universal property, and I'm just rephrasing it in the language of algebraic groups acting on varieties for the universal property. For every G variety V and H fixed point V in G, H fixed point V, there is a unique G map. So map is short now for morphisms of variety. G means equivariant. G mod H to V subject X, which is mapped. This is what you expect. It comes as no surprise. Actually, what is maybe surprising is that I'm not proving it now. Right? I need at least 1 hour to prove this. It doesn't come so easy. One has to do two things. Well, to find the variety that looks like that, G mod H, and then to define its universal property. And actually, this is not a triviality, because after the fact, it is easier than in characteristic 0, but in characteristic P, for example, one can have on this same G mod H, theoretical G mod H, various structures which are not isomorphic. One of them will be universal, be like upper in the hierarchy than all others, and will be mapped on them. But they will not be the same. This is basically considered Frobenius map. Think about just the map of taking the power of P on the field itself. And So this is related, or this is related to the fact that you have non-separable extensions. In characteristic 0, in fact, one need to show that you can only define a unique structure on this G mod H. Still, you need to define G mod H, and what Chevalier does is find some projective representation of G such that H will be the fixator or stabilizer of a certain point, that is, a certain linear line. Slightly more details, what Chevalier does is define a linear representation of G such that, or here's another fact actually that I didn't specify. Every finite algebraic group could be linearly, faithfully represented. It could be multiples of GLN for high enough n, and the image, of course, will be closed. So this abstract notion of algebraic groups is actually a closed subgroup GLN. And but further, given H, we can find a linear representation, irreducible one, may add, such that H will be the stabilizer of a certain subspace. Exactly stabilizer. And then one take some wedge product, making this subspace into a line and pass to the associated projective space, and this line becomes a point, and or if you wish, one can pass already to a certain Grassmannian I didn't discuss right away, and H becomes a fixed point, and you see the cosset space right over there. So you have G mod H. And again, then you will have to argue why you have the universal property, and this is not entirely trivial. I will not waste more time on that, but you should be well. Maybe I will add some more to these things which I will use. Furthermore, if H is normal in G, G mod H as the structure, naturally, of a finitely by group itself. Obviously you believe that, but think about the following example. Take GL2 and take H to be the scalars. G mod H is PGL2. Naturally, you might think of it as a projective variety. So this is already something which is a bit surprising. Well, it is a projective variety. It is indeed quasi-projective variety. PGL is in the projectivization of the 2x2 matrices, but it is not closed. It is open. It is quasi-projective variety. And in fact, it is isomorphic to an affine variety. One has to explain this. Maybe we will do this at some point. Just this example. It is correct in any case. So we have naturally we can pass to protein spaces, but somehow look at the order of things as I presented them somehow. Even this statement over here is just a statement about affine algebraic varieties. You may be only concerned on affine varieties, but still, in order to come up to this theorem, we had somehow to make a detour through the general notion of varieties. In order to define this, and only after the fact to say, hey, and this is affine. Probably one can find shortcuts, but this is the natural way to present things. So really, varieties are crucial notion here in this theory. And for general question, do you have a question? For general H in G, not necessarily normal, one can look at G mod H and look at the automorphism of this in the category commuting with G. And here I'm repeating something that I did say at the very first lecture, that the the normalizer, let's denote n to be the normalizer. Oh, maybe I haven't even said that this is an algebraic group by its own right. So you believe that the normalizer of a group is closed. This is the stabilizer of something in some space, right? And it acts on this variety on the right. Actually, n mod h. And the action. So n is an algebraic group by its own right. H is a group which is normal in it. So n mod h is algebraic group, a fine algebraic group by its own right, and it fits into the picture of us. I can now, I did not on the left now, but it's just the same. I can take this right action of n mod h on g mod h, and this is a fine algebraic group, and this is a variety, and this is an action of an affine algebraic group. On a variety. So these are all things that we need to prove. But of course I will not do everything, but you should at some point read this one. Okay.
Any questions about that?
Now I want to, next time I will discuss measures in variety. Relate everything we said so far to ergodic theory. Let me start very slowly doing it now, just illustrate some examples. Let's make a claim or discuss an example. Let G now be this unipotent group that we discussed. We had at the very first talk. Take the complex point though. Because I discussed things over complex fields. Let L be what I'm sure you understand, GR. Same group with real points over here. So this is a multiplier. Let G act on V. An action of this algebraic group on some algebraic variety. Now let mu, just one note, L is not an algebraic group here. Maybe by the end of the talk, maybe I will say something about other fields. But now I want to proceed. And let mu be a probability measure on the variety V, and let us assume it is L fixed. So you remember we discussed this again. In the first talk, we had this picture, which is more or less an algebraic variety R2, but maybe think of C2, and on the x-axis we had fixed point. All other orbits were just lines. And we discussed at some point, when we mapped G mod gamma into this picture, in a U-invariant way, maybe you remember, we discussed probability measures which are U-invariant on this guy. And we had Ergodicity at the time, and we came to the conclusion that it must be supported on one point. Now I'm not assuming Ergodicity, even though I can reduce it to this case using ergodic decomposition, but I don't need to. My claim is, if this is the case, then mu is supported on the G fixed point. Of V, or in V. So it's actually any invariant measure. Any invariant should be here.
So mu is defined on what sigma algebra?
When I now, it's the Borel sigma algebra associated with the Hausdorff topology. Yes. When I discuss measure, in my mind, I move to the house of topology entirely. The only thing somehow I'm taken, the only thing I'm taken from the theory of algebraic groups is these things. So let me give it. Or maybe observe that the closure, there is a closure of L is G and VL is VG. This is the same thing. If a point is fixed by a group, since the fixator of a point is in any case algebraic, it is fixed by there is a closure. I mean, one inclusion here is clear and one follows from what we just said. So by negation, I may assume this, and by renormalizing, so I can now restrict mu to this bad piece and renormalize and have a measure which is fully supported on this. May assume and actually please make one more jump with me that I can just remove. So I may assume that V is fully supported on the complement of the fixed point by restricting it to normalizing it, and now just clear this from your picture. Replace V by V minus VG.
You are saying that you are removing from V the state of
Yes.
fixed.
Yes. So I'm looking at some open subvariety, and basically I'm replacing my variety with, so I'm not being super formal in writing here, but it is enough, what I'm saying is, it is enough to prove the theorem, it is enough to show that if there are no fixed points, then there are no invariant measures. This is where I'm going. I'm assuming there are no G fixed points and proving there are no invariant measures. I'm supposed to get a contradiction here. By this integrating, so you have this map. Now, maybe I should say, just to define where, in what category my mind is now. The Borel map. So take V mod G, the space of orbits, with the Borel quotient map. This is countably separated. And I can disintegrate measures on it. The space of measures is nice. So actually, I can push the measure from mu from V to V mod G. And it disintegrates nicely. And the fibers are just the G orbits. And take a generic fiber may assume, now I replace mu with that measure on that fiber. That mu is supported on a unique orbit. But what is this unique orbit? It's G mod H for some H. What is G? G is C. Okay. G is C itself, right? It doesn't have any non-trivial subgroup. The only subgroup, the only algebraic subgroup it has is 0 and itself. And there are no fixed points in my discussion here. I throw them away. So I threw them away. So the orbit is just a copy of C. This is a copy of C. And now L R acts on C with with an invariant measure. Again, the action is same. We all understand now R act on C. The action is staying, and we may assume, we may replace the invariant measure we have, we may assume that the measure is supported on one orbit. One R orbit.
Excuse me, could you this place where you take the generic fiber of this quotient map from V to V over G, why can you assume that mu is supported on a unique orbit?
Also, no, so there is another measure, which is the result of this integration, which is supported on. Okay, but the way I'm going here is by contradiction. I want to show that if